Welcome students. We are now ready with the next module of our hypersonic aerodynamics classes. In this module we are going to learn about the shock relations specifically applied to the hypersonic regime. Shock is not a new concept for us. We have already learned about the shocks in our studies of supersonic flow. Here also the similar kind of relation will be applied, and even the concept remains same. Whatever the shock is in supersonic flow, this will remain as a shock in the hypersonic flow also. But a little bit of changes, a little bit of assumptions can be applied, and those relations which we actually learned in the supersonic flows can be reduced to a further simplified form with the assumption of hypersonic flow. What happens? We'll see that as we go ahead. Before we actually go into the studying this shock relation with respect of hypersonic flow, there are basically two things which we must understand, which are related with the supersonic as well as hypersonic. First of all, hypersonic very well qualifies to be a supersonic also, because it also falls in the definition of supersonic flow. But all the changes which are taking place from subsonic to supersonic are giving a entirely opposite behavior. So the behavior of the flow changes drastically, and with a huge contrast when the flow regime changes from subsonic to supersonic. But in the case of supersonic to hypersonic changes, the behavior of the flow doesn't change. So a compression wave or a shock remains further a compression wave or shock only. Only a compression wave becomes further more compressed depending upon the Mach number. So the behavior doesn't change, and there is no any drastic change in the behavior of the flow when the flow regime changes from supersonic to hypersonic. The second thing we have to remember in this context is that the flow properties and all these flow behavior and the phenomena taking place in the supersonic and hypersonic, they differ only quantitatively. The qualitatively they are still the same. There's not much difference. So a shock still remains a shock in the hypersonic flow, but the quantity, the compression the shock can bring about across it is much more and much different in the case of hypersonic flow than in the supersonic flow. Otherwise both remain same, and there is no sharp boundary for the hypersonic flow, so that beyond that we can say it's a hypersonic flow. We know already. Now let us get into the subject matter and try to understand what's going on. There are a few basic questions which can be asked to just refresh your memory of the shock information related which we have studied in your supersonic subject. What are shocks? How they are generated, and why are they called shocks? Simple questions. Shocks are basically discontinuities, and essentially they are actually the compression waves. A lot of very weak compression waves are joined together, and the changes in the property they bring across them become finite, so they become shock, and it got discontinuity because the changes are abrupt in a very small span of a small space, a very thin space. The changes are very large, so they are called discontinuity. They are generated because of the pressure which is lying ahead. A high pressure lying ahead normally creates the shock, because flow takes place from higher pressure to lower pressure, and if the high pressure is lying ahead of the flow, then definitely it's going to kick back and a shock is generated. And definitely mechanisms are also different, because in the case of oblique shock, when a supersonic flow turns into itself, it generates an oblique shock, and normal shock is generated because only a high pressure lying ahead. They are called shocks because when somebody is traveling with the supersonic speed, any information lying in the flow domain comes to it as a shock. because these information basically travel in the pulses and in the sonic pulses, and this sonic pulses travel with the speed of sound. So if a body is traveling with the speed which is lower than speed of sound, then these information reach to the body well in advance, and body can react, and body can actually treat this information very nicely and go ahead. Now if the body itself is traveling with the speed of sound, that these information will not be able to reach to the body in advance, so the information will be actually coming as a shock. A sudden change will come there, and then this is some discontinuity will be created, what we call shock actually. These are the basic information about the shocks which we learnt in during our supersonic treatment. It is advisable to the students that they should brush up and they refresh all these information before we actually get into the hypersonic domain and we study the shocks. Now shock types, before we actually get into the shock relation, let us just see the shock types. One of the type of the shock is an oblique shock generated in the flow when the flow has to change its direction. So oblique shock is basically generated when a supersonic flow turns into itself. It turns the direction, it's very simple, and when it turns into itself, and in this fashion the space available for the flow after the shock to actually flow and take place, it is smaller. So this space is larger, this space is smaller, so flow has to be compressed to maintain the continuity. So flow gets compressed, and then we get an oblique shock available here. This theta is theta is actually the deflection angle, the angle by which the shock is deflected, and beta is the wave angle at which the shock generated remains inclined with the original flow. Remember, it's original flow, or the upstream flow, or the free stream flow. This is actually beta. This is oblique shock. A normal shock is generated when a high pressure lies ahead, and this pressure kicks back the flow, and a standing normal shock is generated. The normal shock is the strongest shock, and it brings about the large changes in the flow properties, and which is much more than the oblique shock. And the flow across a normal shock is always subsonic. The supersonic flow becomes a subsonic flow. In the case of oblique shock, we have two types of oblique shock. One is a strong oblique shock, other is the weak oblique shock. And in a strong oblique shock, the flow again becomes subsonic after the shock. In the case of weak oblique shock, flow comes down, the Mach number comes down, the speed slows down, no doubt about it, but the flow after the weak oblique shock still remains a supersonic flow. That's the only difference we have seen this thing. Shock is a very infinitesimally thin region in which a very chaotic motion is observed, and a lot of viscous dissipation is observed, so the temperature goes very high, and the thermal conduction is also observed. Shock is basically a very thin, of the order of 10 to the power minus 5 centimeter. So this shock cannot be actually observed by the naked eyes. Only with the special arrangement we can actually visualize it. Are shock really discontinuous? This is one of the basic question. Normally we take shock as discontinuous, and we also define the shock as discontinuity, but shock basically are discontinuous if you have a macroscopic view. Macroscopically we can see that in a very thin region, which is almost a thin line, and across which the flow properties jump from low value to very high value in the case of pressure, temperature, or density, and some value change from high value to low value. So it looks like the shock is actually discontinuous. But if you look into the microscopic level and see what is going inside the shock, then we find that there is no discontinuity. There is a complete continuous curve we can see in all the flow properties, which are going very high or coming down, and they maintain the discontinuity, although their rate of increment or decrement is very high. So it looks like discontinuous if we have the macroscopic view, but in the microscopic view they are actually continuous. Now let us just go into the shock relations and try to see how these relations can be actually modified and applied to the hypersonic regime with a simple format. Let us take the pressure ratio first. This pressure ratio is giving the exact value of the of the pressure ratio when there is a oblique shock existing. Beta is the oblique shock angle. It's the wave angle. So this gives the exact relation. Now we just apply the hypersonic assumption by assuming that since the Mach number is very high, this m1 square and sin square beta will be much larger than 1. So this can be actually this one can be reduced. So when we apply Mach number to be infinity, in fact it's not infinity but very large, so large enough to be treated as infinity, then this equation reduces to this, so it becomes simplified. So 2 gamma b gamma plus 1, first this high value negates this value of 1, and then this high value as a whole negates this one also. So finally we get a very simple equation, and our assumption is m square sin square beta is greater than 1, so this one is negated. We can do the similar treatment with the density ratio. Here the density ratio, and this is the exact relation of the density ratio across an oblique shock. Again, this m square sin square beta is very large, so so this whole thing can be larger than the 2, so 2 is negated. Once the 2 is negated, these m square sin square beta, they cancel each other. So finally, for the hypersonic for the high Mach number, density ratio turns out to be like this, and this can be actually a little bit surprising because there is no relation of Mach number. So in the case of hypersonic regime, the density ratio loses its dependence on the Mach number and becomes free of the Mach number. Temperature ratio can also be found out, that T2 by T1, we know that this is the equation of a state. P2 by rho 2 is equal to R into T2, so R is cancelling. So T2 by T1 is equal to this, and now we already have found pressure ratio and density ratio. We apply them first here and put them here, and this is value we are getting only after applying this. We have just put this value, the reduced value of pressure ratio and reduced value of density ratio, we have put it here, but this value is already reduced. So whatever we are getting here is actually after applying the Mach number limitation to be very high in the case of hypersonic flow regime. So now after doing this little manipulation, we get this to be like this. Again, the reason was m square sin square beta we get greater than 1, but now we cannot reduce further by applying this assumption, so this remains like this only. The velocity ratio, we just try to see how the velocity ratio changes. Velocity ratio, we have normally in the case of oblique shock, we take the velocity triangle upstream or downstream, and then we just reduce them and treat them as upstream and downstream velocities, and we find the relation across them. In this case, we are also treating the velocity, but we are having little different concept here, that the velocity on the upstream we are not resolving, we are just keeping it as it is, and we believe that, and then velocity on the right hand side, which it is downstream velocity, we resolve in mutually to perpendicular direction, and the vertical these perpendicular directions are one along the velocity itself, the upstream velocity itself, and other one perpendicular or normal to the upstream velocity. Contrast to our earlier treatment of the shock, of the oblique shock, where we normally resolve the velocities along and perpendicular to the oblique shock, but here in this case we have resolved them only along and perpendicular to the velocity. This is v1 velocity. Now horizontal velocity ratio. So this is the ratio, and this is exact relation. What we got is the in the case of oblique shock, and again remember this u2. This is the same u2 which is along v1, not along shock. Now we apply the limit of Mach number to be very, very high. So this value is more than 1, so this 1 is removed from here. Now this since 1 is gone, this m1 square can be cancelled with this, so we can be, so whatever we get is 2 sin square beta by gamma plus 1, and now this is a very small value, it's not very large value, so in that case it cannot be ignored, or 1 cannot be ignored compared to it, so this whole thing remains here, 1 minus 2 sin square beta by gamma plus 1. Similar treatment we do to the vertical velocity ratio also. This is the exact relation in the case of V2 by capital V2. This capital V2 is we know that it's actually the upstream velocity, and this is the resolved velocity perpendicular to V1. Now apply this hypersonic Mach number limitation, that limit m1 tends to infinity. Then this value is much more than 1, so 1 goes off. So what we have is now m1 square sin square beta. Now this m1 square, this 1 square, they cancel each other. So we have sin square beta into cot beta, and now cot beta itself is the is actually cos beta by sin beta. The one sin beta cancels here, so we have this value available here, and then this can be changed like this. It's a trigonometric relations. We know that 2 sin beta into cos beta is equal to sin 2 beta, then gamma plus 1. This value again, you can see that velocity ratios again are not depending upon the Mach number. So as the Mach number goes very high, the dependence of these velocity ratios and also the density ratio we saw on the Mach number loses continuously, and they try to attain a fixed finite and value rather than going very high. So now with infinitely high Mach number assumption, we observed by treating these ratios for the infinitely high Mach number, we observed that pressure and temperature ratios attain infinitely high value because they contain Mach number still in the reduced equation, so they will keep increasing as the Mach number increases. But density and velocity ratios attain a fixed finite value because they don't have Mach number in the expression anymore, so they will attain as fixed finite values once the high infinitely high Mach number relation is applied. Pressure coefficient, let us see how it goes ahead. This is the definition of pressure coefficient, and P2 minus P1 by V1. Actually pressure coefficient is defined by the on the basis of free stream quantities. So we are just treating this P1 and P2 as the upstream quantity of the shock, but they can be taken as the free stream quantity also. So in the subsequent chapters we'll deal the free stream quantity with the subscript infinity, but here we are taking P1 and D1 and the Q1. Q1 is your dynamic pressure in the free stream with respect to the free stream local conditions. Now this Cp is actually being calculated at the point 2 where this value P2 is there. So P1 and Q1 are independent, so it is always a reference condition, and P2 is the point where Cp is being found, and then this relation defines the coefficient of pressure, and these are anyway this is the dynamic pressure at the in the free stream condition. Now this dynamic pressure can also be transformed into and expressed into the terms of Mach number, because Mach number when the velocity goes very high, we normally deal with the Mach number. So this Mach number, this quantity can also be expressed in the terms of Mach number. Reducing from here to here takes a little bit of 2-3 steps. Students can do this thing, and those who are not able to do will see in the classes. So from here to here can be easily reduced, and we'll be using this dynamic pressure in the terms of Mach number only. That is much more useful actually and more handy to use. Now treating this coefficient of pressure, this is the definition, and this definition turns like this. We just replaced Q is equal to this 1 by 2 this value Q in the terms of Mach number and pressure. So 1 by 2 gamma P1 M1 square, so 2 goes up and P1 goes inside, so this P2 by minus P1 becomes like this. Now we know already P2 by P1, so we just put P2 by P1 like this, and applying P2 by P1 minus 1, we get this value. There is little more manipulation into this. After putting P2 by P1, and these are exact value. What about the exactly we have received from P2 by P1 across the shock, especially oblique shock? We put the exact value here, and this and do little manipulation, then we'll get coefficient of pressure like this, then now we are ready to apply the hypersonic assumption. In the hypersonic assumption, we apply this is the same equation, and with the limitation of Mach number going very high in the and we can apply is equal to infinity, we get this value vanishes because m square will be very high, so it becomes 0. So finally this is the relation. So if you know the that wave angle, we can actually find the coefficient of pressure. Equations are reducing very simple after applying this assumption that Mach number tends to infinity. Theta beta m curve, you know very well what is theta beta m curve. This theta is the deflection angle, beta is the wave angle, and m is basically the Mach number. So this is the free stream or the upstream Mach number. And when these curves are drawn, we draw them. This is the equation. This is the equation. Theta beta m curve, theta beta and m relation. So m square is there, theta and beta also available. And one thing has to be actually realized here is that theta, this equation tells that it is actually explicit for theta. So theta can be kept one side and beta and m both on other side. This is possible to do this thing, so it becomes explicit in theta or for theta. So the theta can be expressed in beta and m. But if you try to actually express beta in terms of theta and m, this is not possible. This relation is not possible to be reduced in that form, so it is implicit for beta. Now we'll just see that how to actually modify it and make it explicit for beta also, but definitely we'll have to assume something. This is the theta beta m curve. This is the deflection angle and theta, and the wave angle beta, and this is the m. For various m, we are going to have one curve. So for every Mach number, we have one curve. This picture gives one extra information to us that for high Mach number, this is the for high Mach number and low deflection angle, beta is very small. So if theta is small, so body is cylinder, you can say that for the cylinder body case. If Mach number is very high, then beta also is very high. In that case, we can not only apply the high Mach number assumption, we can also apply the low angle assumption. So let us see what happens. In the case of low angle approximation, the sin beta is beta, we know that, and cos 2 beta or cos beta both are equal to 1, and tan beta equal to tan theta equal to sin theta equal to theta. In fact, in the case of low angle, we assume these assumptions. Now let us apply these assumptions to our theta beta m curve relation. First of all, in the theta beta m curve relation, first apply this small angle approximation. It is here. So when you apply the small angle approximation, all this sine and cos vanish. This cos 2 beta becomes 1, cot beta becomes 1 by beta, and sine b square beta becomes beta square. So the small angle approximation has been applied here. Now we apply the high Mach number approximation. In that case, if the Mach number is very high, then this will be very high, and this will then 1 will vanish. To be high, so 1 is vanished here. And the moment 1 is and this also is very high, so 2 is vanished. In that case, these m square will cancel each other, so we have, and beta will also, 1 beta will be cancelled from here, so we got 2 beta by gamma plus 1. Very simple relation after applying high Mach number approximation. So we got a relation theta is equal to 2 beta by gamma plus 1, and by looking this is telling that these are actually a linear relation. So initially we saw that the relation theta beta m curve relation is explicit in theta but implicit in beta. So we cannot write beta in the terms of a Mach number and theta, but here Mach number has even vanished, and once you know the theta, we can easily write beta, and there's a linear relation. We can easily write. But one more information is coming here, is that again this expression is free from Mach number. So if the Mach number goes high, theta attains for a given theta, beta will attain some particular value. It will not go beyond that value. So for high Mach number and low angle involved, we get this relation. So we have this is sentence telling that we have applied two assumptions: high Mach number and low angles involved, and this then will be able to actually express beta in terms of theta. So now beta becomes explicit. So again we are writing like this in terms of beta. For gamma is equal to 1.4, we find that beta is just 20% more than theta. So they both are very close to each other. This actually confirms our thin shock layer concept. So beta is just 20% more than theta, and one realistic value we have seen this picture earlier also. For a Mach number 36 and deflection angle 15 degree, the shock angle is just 18 degree, and this confirms that beta is actually just 20% more than theta, and it means that even Mach number 36 is actually large enough to be treated as infinity, and this relation that 1.2 times theta, beta is 1.2 times theta is applicable here also. 15 into 15 if increased by 20% becomes 18 actually. Now let us summarize it, that in the summary that P2 by P1 is actually 2 gamma by gamma plus 1. This is the reduced form. We have reduced it from the exact form, and rho 2 by rho 1 and T2 by T1 also, these are the reduced forms. So these pressure ratio and temperature ratio, they contain Mach number in their expression. So as the Mach number increases, these values will keep increasing and will become very large at a very high Mach number. On the contrast of it, that density ratio is not having Mach number. So density ratio will lose the dependence on Mach number as the Mach number goes high, and will actually attain a fixed finite value at a very high Mach number, and that finite value will be given by the by this expression. If we have this information about gamma, then it's easily calculated. The velocity ratio also, the reduced format are given like this, and this is the coefficient of pressure. Again we can say all these are actually free from Mach number, so they will try to attain a constant and finite value as the Mach number goes very high. And beta is given like this. Beta is also attaining some kind of constant number and finite number for the for a very high Mach number, and we have assumed two assumptions here, that hypersonic limit for high Mach number is there, plus angles are also small. So after assuming these two assumptions, we find that we can actually linearize theta and beta, and we can express beta purely in the form of theta. So beta becomes explicit now, which was not the case in the case of theta beta m curve in the exact situation. Actually our requirement is always beta, because theta is something physical angle. We can actually physically measure how what will be the deflection of the flow, but beta is actually aerodynamic concept is there, and there's aerodynamic invisible discontinuity is existing in the flow, and that angle is actually its angle is actually the beta. Its inclination with respect to the free stream velocity is flow is actually the beta, so it becomes difficult. Now if you know the theta, beta can be found very easily. Shock relations with the similarity parameter. Now we know the shock relations already. Shock relations can be actually derived with the information and with the help of similarity parameter also. What the similarity parameter is? M1 theta, that we call actually similarity parameter, hypersonic similarity parameter. Now M1 is still that high for the high Mach number. M1 is free stream Mach number, and theta is the flow deflection angle. And where we are making two assumptions for all the derivation and the treatment of the relation. We will try to assume two assumptions always. One is that Mach number is very high. So if the Mach number is high, we can treat it actually equal to infinity, or sometimes it is very high, but sometimes we treat it high but not high enough to be actually treated as infinity. But we are treating right now it's very high, and we are treating it to be infinity also, and the theta involved, the flow deflection angle, is very low. So we have two different or two opposite assumptions in these two cases. Now let us just treat this for the theta beta m curve and see how it goes ahead. Again, this is the theta beta m relation, which is the exact relation, and no assumption has been made till now. Now we make a small assumption of the small angle, and then beta, the trigonometric relations of beta is actually vanished, and cot beta and the sin beta and cos beta are all giving their corresponding values for the low angle assumption. Now this can be actually just manipulated further. This step is nothing but just theta multiplied by beta, and then these two comes down to this, and then this whole thing is multiplied here. So this is just a little manipulation. It's not manipulation, as a matter of fact, it's just a rearrangement of the parameters and the terms, and now this is written like this. Now we further apply the hypersonic assumptions that Mach number is very high. If Mach number is very high, then this will be large enough. This will be large enough to actually make this actually more than 1. Now one thing has to be careful here, that Mach number is very large, so this becomes large, and 1 is ignored here. So what is written here, you can see that theta beta m square by 2, this whole thing by 2, but this is written as it is. Despite big Mach number very large, the beta, the small value of beta makes it still comparable with 1, so we cannot simply ignore this thing. So high Mach number assumption is applied, but high Mach number is not high enough to actually make this m1 square beta square product as equal to is much larger than 1, so 1 is not ignored here, so they is still maintained. Now again we write the same relation from the earlier slide, and after little rearrangement, and we find that this can be turned into this relation, that beta by theta square and all these things. So this is basically a quadratic relation for with the variable beta by theta, and this equation can be solved quadratic with the quadratic fashion. So this is the quadratic fashion. You can, this is in the form of a plus bx, ax square plus bx plus c. So now this x is equal to minus b plus under root b square minus 4ac by 2. So this turns out to be like this. Now we have got already the coefficient of pressure ratio. Let us see the pressure ratio directly. Pressure ratio is this one. Again, this is the exact relation. We apply the low angle relation first. So if low angle is there, this becomes actually less than this becomes actually beta. Now this is actually strong. This is good. This is very large, but not a smaller value of beta is making it finite enough to actually consider comparable to 1. So 1 is not ignored here. Now beta square value is required. So we just now use the relation we have found, the beta for the beta. Now what we found actually is beta by theta, not the beta square. So either we just square it and then find out and then put it here, or we just use some different method which we are going to show you just now. So what we do is, this is your beta by theta relation, and we just put this beta by theta here in the case of the quadratic relation for the beta by theta. This turns out to be like this, and after manipulating and after solving it, we can find that beta square can be actually given like this. This is the beta square, and this is what is our requirement. That's what is involving in our pressure ratio relation. So we just put the whole beta square in this value, and we got this kind of expression. So this expression is there, which can be little manipulated. Again, this is not manipulation; it's just more of arrangement. So if you just arrangement and just cut down the some similar values, then it becomes like this. And this gives a very pleasing feeling, because now we have this m square theta square and gamma. So m1 is this is nothing but the hypersonic similarity parameter and this gamma. So now the pressure ratio has become simply the function of two variables. One is the hypersonic similarity parameter, and another is gamma. So once we know all these things, we can actually find the pressure ratio. This is the pressure ratio, which can be reduced in this format, where m1 theta is taken as k, which is the hypersonic similarity parameter, and this actually this we should not forget. This is what we are actually going to use when the time comes and so start solving and analyzing the hypersonic cases. The pressure coefficient again. So we come to the pressure coefficient and see that this is our pressure coefficient in the terms of Mach number, and this is the pressure ratio. We have already seen that this is not very difficult. A student can derive it. I think students should derive it, so that they will be actually feeling comfortable with this thing. Now this is the pressure ratio we have found just now in the case but in the terms of hypersonic similarity parameter and the gamma. So now this pressure ratio, if we just apply and put this in the case of CP, then becomes like this. Just P2 minus P1 minus 1. So this goes minus 1. So this whole thing in the bracket is actually equal to this two terms only. So we put this term here. Now we have k square here and k square there. So this theta square, this just 2 gamma by k again goes inside. So sorry, the gamma k square goes inside. So this what we remain is actually gamma plus 1 by 4, because this gamma and this k square cancel each other. 2 theta square remains outside, and this goes inside. This turns out to be like this. So what we actually normally have got is this Cp by theta square is actually a function of only k and gamma. The question, no matter how complicated it looks, since it is involving only two parameters, only two variables, it becomes very easy to deal with and treat. There is a little homework I have prepared for the student, that a student can actually derive this. This will give them little more confidence, and they will be able to able to see how this velocity ratio is actually derived. Again, this velocity ratio is along and perpendicular to the v1, the initial velocity, and then these are the exact solution. This is not the approximate solution. There is no assumption has been made in this thing. So a student should take some time, and actually they should draw this relation, and it will give them a huge confidence. Now in the next we have in the next module we'll try to take up the expansion waves in the hypersonic flow. Of course, this is also the supersonic phenomena. So in hypersonic flow, compression waves are coming, so expansion waves also will come into picture, and we'll deal that in the next module.